All right, hello everyone. Welcome to the induction cooking demonstration. We're going to start out with an overview of how induction works from our chapter physicist, Craig. So Craig, let me turn it over to you. And after you get done with your explanation for how induction works, then we'll do the demo of the stove.
Okay, very good. Let me get this going. Okay, so if you took the cover off your induction stove, this is what you'd see underneath. There's a coil here, electrical coil, a fan, a heat sink, and a bunch of circuitry. And this electrical coil is the heart of the induction process. It's half of a transformer. So current is put through here, and it generates a magnetic field. That's a standard physical phenomenon. And this illustrates, here is a coil generating this alternating magnetic field. And that alternating field is picked up by another coil. This would be the second part of the transformer. And for an induction stove, that's the pot. So as you can see here, this is not very well aligned with the coil. And so it's missing a bunch of the magnetic field. So on your stove, you want to take this coil, that is the bottom of your cook pot, and put it as close to this, back up, as close to this coil as you can. And you can see here, this has 5 turns. This has many, maybe 30 turns. It turns out that the current induced in this coil or in your cook pot depends upon the ratio of these 30 turns to the single turn that represents the bottom of your cook pot. So if there's, say, 1 amp going through here, you'll have 30 amperes of current going through the bottom of the cook pot. So what does that do? Well, here's my drawing of a cook pot and the base of the cook pot, which is the important thing. And an alternating field in the coil in the stove then generates currents that flow in this bottom layer of the pan. With a transformer, you want to minimize those currents, but for our purposes, for an induction stove, you actually want to maximize them. And we want to have as much power generated, as much heat generated in here as possible to get this part hot to cook the food. Well, it's like putting water through a garden hose. If you have a large diameter hose, that is the full thickness of this base, it doesn't cause much resistance to water flow. If instead you're restricting the water flow to just a small hose, then you have a lot of resistance, and it turns out a lot of power dissipated and heat generated. So we could either make the cook pot base very thin, but that would be impractical, or we can go to a high frequency of current in the induction coil. And that's what induction stove manufacturers do. They go to a high frequency, about 24 kilohertz is the standard. Even higher would be better, but the electronics becomes very costly. So this is sort of a compromise. So at high frequencies, the current doesn't flow through the whole base of this pot. It flows only in a little bit here, right at the bottom surface of that base, to a skin depth delta. That's the distance here over which the current flows. And that, as it turns out, is equal to quantity rho, which is basically how good a conductor the material is. If it's a good conductor, then the resistivity rho is low. We want to go as high a frequency as possible, but we're limited to 24 kilohertz. And the final term here, mu, represents permeability. And that basically says, is the material magnetic or non-magnetic? If you can stick a magnet to it and it clings to it, then it's magnetic. Otherwise, it's non-magnetic. So to reduce, to make that skin depth just as small as possible, then We want to go to a high frequency, which is not under the user's control. You want to use a cook pot with a high permeability. And to make the skin depth small, you want to go to low resistivity, but don't forget the power generated is the current basically times the resistance. So in fact, when you put all those terms together, it's the resistivity divided by the skin depth, or here's the bottom line, that the surface resistance, which is what you want to maximize, is equal to the frequency, the resistivity of the material, how good a conductor it is, and the permeability, is it magnetic? So here's an example of several different materials that might be used to make the bottom of a cook pot. Aluminum and copper are very good conductors. You can see the resistivity here is quite low, but we want something high for this reason over here in the square root. So from this, a stainless steel, this is a non-magnetic stainless steel, has the highest resistivity, but we also want high permeability. And this stainless steel, being non-magnetic, doesn't have a high permeability. So that advocates then for going to something, either a carbon steel or a magnetic stainless steel. The carbon steel, because it has lower resistivity, has the smaller skin depth, but when you take into account all the factors here, even though it has a smaller skin depth, this stainless steel wins out. It has the highest resistance, which is what we want. So what does that mean? We want, with the cookware that you need to use on an induction stove, then is going to be a magnetic material, like an ordinary carbon steel that might be used in an ordinary cook pot, or a magnetic stainless steel, but you would want to stay away from. And if you have stainless steel pans that are non-magnetic, they aren't going to work, nor will aluminum or copper pans.
So Craig,
Yeah.
what is permeability of the magnetic, whether or not it's magnetic, or is that
Yes,
something else?
yes. So here is the permeability. So you can see these two materials are magnetic, and they have a very high permeability, 200 versus 1.
Okay, and then can you say just a little bit more about skin depth? What is that a physical characteristic of the pan?
It's a characteristic. It depends on all these factors. So part of it's a characteristic of the pan, the resistivity, how good an electrical conductor the pan is, and how good a magnetic material it is. The frequency we don't have a control over. That's what the manufacturer has picked. So in choosing a pot, you have control over these two factors, and the ones that give you the best power would be a steel. A cast iron would work well too. It's not listed here, but that would work well too. A steel or a magnetic stainless steel or cast iron, all of those being magnetic materials.
Okay, and then one more question before you move on. So that final column where you've highlighted the highest number is 3.5.
Right.
So does that imply that cooking with that type of pan as opposed to a carbon steel pan would be slightly more efficient?
Not necessarily more efficient. It would probably give you slightly more power. So if you want to boil water quickly, you're probably better off with a stainless steel pan than with a carbon steel pan.
Okay.
But
Thanks.
there's so many other factors that come into play here that I wouldn't get too concerned about nuances. You know, how big is the pot compared to the heating element? Is it centered on the heating element? That sort of thing.
Okay.
And how close is it to the heating element? Okay, so let's look at efficiency. This is really the best efficiency you can get. All the power goes into the water if you're boiling water, but clearly it's not a very practical tool to use for cooking a dinner. So the Department of Energy has devised some standard tests to compare different technologies, And in particular, we'll look at natural gas, a standard electric coil stove, and an induction stove. And in terms of the efficiency, that is what I'm calling wall plug efficiency, which really refers mainly to electrical technology. The electric coil and the induction coil are comparable. As I say, there's so many other factors that I wouldn't worry about a few percent one way or the other. Natural gas is much less efficient. But if you figure in the fact that the electricity that you need to run these two electric technologies comes from a power plant, and if that power plant, for example, is using natural gas itself, then you have to take into account the inefficiency of the power plant. Their standard number is about 38% efficient. So if you compare then the primary fuel that you're using, gas wins. But again, there are a lot of other factors. Gas, based strictly on efficiency, a gas would win. But we have to recognize that gas is a fossil fuel, that it's less safe than electrical technology. It creates pollution, both indoor pollution and regional pollution. So there are other reasons than efficiency for wanting to go to electric and particularly to induction cooking.
If your source of electricity is solar panels on your house, then your fuel source is known to be.
Efficiency doesn't really, is not even a concept that you want to use. The sun's going to shine no matter whether you're taking advantage of it or not.
Right.
So yes, definitely. If you have solar panels, then you are indeed emitting no fossil fuels in using either of these, whereas you would with natural gas.
Mm-hmm.
Okay, then just finally here, this is a quick chart of comparing these three different technologies. As I said, wall plug efficiency, gas is much worse than conventional or induction. Primary fuel efficiency, then the natural gas actually wins out over these two, assuming you're getting the power from a natural gas powered natural gas fuel power plant. Pollution, gas is poor. Both conventional and induction are good in terms of pollution. They, in fact, create no indoor pollution. Heating time, induction heating is extremely good, much better than conventional electric, because you're heating the pot only. You aren't heating the heating element that a conventional electric stove would use. In terms of response time, that is, if you turn off the power, gas is excellent and induction is excellent. Poor, again, you've got to wait for that heating element to cool down before you actually stop heating the food. And cleanup depends, it's definitely excellent for induction heating because you have a nice smooth surface. If it's a conventional one with conventional coils, then that's not so good. If you have one with a smooth surface, then it's better. And gas is again not good from a cleanup standpoint. So I think that's it on my part. I'll turn it back to you, Jenny.
Okay, excellent. Well, thank you so much, Greg. Okay, so now we're ready for the demonstration part. So for this demo, I'm just going to boil water. I've got 1 quart of water, which is about at 61 degrees. And so we're going to turn on the stove and then start the timer to see how long it takes. Turn it on and start our timer. Okay, so the main reason that we switched to an induction stove is, well, apart from the fact that our gas range was old and starting to have some problems, is that it's all electric. And we know that in order to get off of fossil fuels, we need to electrify everything. That's one of the main components of Ann Arbor's A20 carbon neutrality plan. So even though right now our source of electricity might be coming from coal and natural gas, when it's 100% renewable, then our electric appliances will not be using fossil fuels. Some of the benefits of induction are that it's fast and very responsive, similar to natural gas, and unlike traditional electric. After this water gets boiling, I'll show you just how quick it is to, respond when you turn the temperature on, low or high. It's also safe. Natural gas ranges are a big source of indoor air pollution. In fact, they can create levels of indoor air pollution that would be considered illegal if they were outside. And there's also a lot less fire risk due to no open flames. The induction stove doesn't generate extra heat, so that it's a lot cooler, especially in the summer. It doesn't heat up your kitchen. In fact, if you turn on the burner, you can put your hand on the burner because it doesn't, it's not creating heat from the burner. It's heating up the pan directly. It's also easier to keep clean, both because the surface is flat and smooth, and also because boilovers don't make as big of a mess. In fact, if you want, you can put a paper towel underneath your pot, and that doesn't affect its ability to heat up. And that if something's going to boil over, that helps keep it clean. Some of the possible drawbacks are that you do need to have cookware that is magnetic. It's easy to test if yours is, if it'll work, just sticking a magnet to it. Of course, you want to stick it on the bottom. And looks like we're about at a full boil right now. So that's 3 minutes. To see how quick it is to respond, I turn it down and see how quickly it responds. Turn it back up. So yeah, as far as the magnetic cookware, so happened that we already had magnetic pans. We didn't need to buy new ones, but a lot of manufacturers will provide rebates on cookware, so that it's a little bit cheaper if you do have to buy new cookware. Sometimes it makes a little bit of a humming or a buzzing noise, so that's just something that you need to be aware of. It doesn't bother me at all, but you might notice a little different sound when it's cooking. And you also need to have 220 electricity, so it's possible that you would need to have a new outlet installed near your stove if you don't already have that type of outlet. So that's it for the demonstration of induction. Hope you enjoyed it.